You buy a top-tier commercial printer and load it with premium ink, yet the final print still emerges as a blurred, bleeding mess. When this happens, our immediate reflex is to troubleshoot the hardware. We run cleaning cycles, realign the print heads, and check for mechanical errors. But the machine's diagnostics report back healthy. The hardware is executing its programming perfectly. If the machine is flawless, the failure is occurring elsewhere. The cause lives in the microscopic physical space between the printhead and the material. To find it, we have to shrink down and follow the journey of a single drop of ink. Flawless print quality depends less on hardware maintenance and more on mastering the invisible physics of the room. Every drop of ink begins at the capping station. This is where microscopic preparation determines whether a print will succeed before the ink ever moves. In this nozzle tube cross-section, a trapped air pocket is a critical obstacle. When pressure applies to eject ink, the bubble behaves like a spring. It compresses, absorbing the force, preventing the ink from leaving. Because this specific droplet is choked at the source, the error propagates. One trapped bubble leads to a sequence of missing dots across the entire print batch. Mechanical perfection at the computer level is useless if the micro-fluidic dynamics fail at the point of launch. If the droplet successfully ejects, it enters the open air as a perfectly formed sphere. Immediately, it encounters its first external enemy, ambient static electricity. Horizontal lines represent the room's electric field. Because the ink carries a charge, static acts like a magnet, pulling the drop off course. Its trajectory bends, landing entirely outside its designated target square on the grid below. To the naked eye, these microscopic misses appear as missing dots, the tiny blank gaps that disrupt a solid field of color. This also explains color shifting. When a droplet lands just a few microns away from its intended position, your crisp colors turn into a misaligned, muddy blur. The air between the printhead and the canvas acts as a volatile field that actively alters the droplet's path. Finally, the droplet survives the turbulent flight and physically impacts the target material, ending its journey. The result of this impact is dictated by a concept called surface energy, how a material interacts with fluids on a molecular level. In these surface cross-sections, the left material has high surface energy. Strong molecular forces pull the ink inward, keeping it sharply beaded. On the right, lacking that holding power, outward forces pull the ink uncontrollably deep into the structural fibers. This loss of structure is why colors appear faded or bleed into one another, regardless of the ink quality. The material's molecular state dictates the final shape of the ink, often overriding the printer's intended design. Let's pull back from the microscopic level and look at the printing facility as a whole. Standard maintenance only addresses the internal mechanics. It ignores the external environment that accounts for most printing failures. Fading, bleeding, and misalignment are physical reactions driven by microcontaminants, static, and surface energy. To achieve flawless output, you have to transition from being a machine operator to an environmental controller. In the next video, we will detail the specific engineering steps required to stabilize your room and defeat these invisible enemies.